Okay, so what was the key thing we need to do for binary search? Where everything needed to be sorted. But we haven't talked about how you actually sort something to begin with. There are a lot of sorting algorithms. If you go on Wikipedia, it just keeps going. And people come up with new sorting algorithms as time progresses for different attributes. We're going to go through probably the 5 most classic sorting algorithms, 2 of which are still in common use. The other 3 are basically a build-up to the 2 that are common. And so we'll start with each one. We talked about big O, that's nice, we don't care about those graphs anymore. Sorting algorithms. The first one is called bubble sort. And bubble sort is nice in that it's the easiest one to code. Am I recording? Good. Whew. Easiest one to code. It's not so nice in that it's probably the worst in performance. Oh, this is already sorted, so it's kind of silly to sort this.
Yeah, we did.
Yeah, we already did. All right. So the idea is that your item is going to bubble up the array. So you can think of the array one way or the other. The top is the lowest, the bottom is the greatest. And so your eventual goal is to make it sorted. But how does it do it? Well, excuse me. It starts by, let's see, compare and swap. What it's actually going to do is move the largest item to the bottom. And it does that by comparing things one by one, aka it's bubbling. I don't like this picture because it's bubbling down in this picture as opposed to bubbling up, which is what you usually think of it. But right now the bubbles are going down. They're the anti-gravity bubbles. Yeah, that's it. So we're going to bubble down. 10 and 7. 10's bigger, so it needs to go down. Compare the 10 and 9. The 10 is not bigger, so the 9 stays. Compare the 19. The 19 and 5. The 19's bigger, so you swap the 19. You compare the 19 and 16. The 19's bigger, so the 19 swaps to the bottom, and now the 19 is in the correct location. All right, that was the first iteration. Let's do it again. Round 2. How many rounds do you think there are? In rounds. And how many comparisons do we do for every round? In. So what type of algorithm is this?
In squared.
Boom. Everyone got that? That's just be like that. That's it. You're done. Big O. Great. What?
That's a lot of Mortal Kombat.
It is. Now I will not be able to get the Mortal Kombat theme from the movie out of my head. Nice. Well played. They played that song so many times in that movie. All right. Anyways, compare the 7 and 10. Don't need a swap because the 10's already bigger. Compare the 10 and the 5. The 10's bigger, so swap it. Compare the 10 and 16. The 16's bigger. Don't do anything. The 16 is now in the correct location. All right. Let's do it again. Compare the 7 and the 5. Hey, look, the 7's bigger, so swap it. Compare the 7 and the 10. The 10's already bigger, so leave it. We're done with that one. Let's do it again. And then 5 and 7. 7's already in the correct location, so we're done. Because you could run the algorithm on an array of one element, but the nice thing about an array of one element is that it's already sorted. Tricky.
Somehow finds a way to unsort.
Unsorted. That sounds like a meme, like that meme. I forgot what that. Yeah. Tries to sort, can't sort one element. Okay. So, bubble sort contains nested loops. Wow, we didn't even talk about how this works. Int bubble sort. Don't call it b sort because that could be something else. Can't make the array constant because we have to manipulate it, but we can make the size constant. So for int I equals 0, I is less than size, I plus plus. I'm going to just go autopilot right now because I've written this algorithm so many times. Actually, let's just start this at 0, just to make our lives easier. All right, if ARY sub, let's see, what are we going to do? J, we'll do J minus 1 is less than, we'll do greater than. arrow sub j plus 1. Then we need to swap them. We'll make a temp. Look at this, guys. It's amazing. All right, I'll make you fill this part out. We need to swap arrow sub j and arrow sub j plus 1. So we have a temp that's arrow sub j. So what do we do next? Since we've got a temporary of arrow sub j, let's go ahead and overwrite what arrow sub j is. And what should that be equal to if we're swapping? Go for it. Go, go, go. I just wrote all the hard parts of bubble sort. As hard as it is. And then now we need to set arrow sub j plus 1 to something, which is the temp. All right. Let's see if that worked. All right, someone start writing some numbers that are not sorted. Yeah, sure, 27. Come on, let's at least get 8 in there. 8 elements, I mean. 1, 2, 3, 4, 5, 6, 7. There, perfect. All right, I got it from here. It's okay. We'll call bubble sort on to sort, passing in the size of 8, and then let's go ahead and print it out. To sort sub I. Now that's all we need for there, and then let's make a little. All right, let's see if all that works the first time. It did. Okay, great. All right, bubble sort is going to have one and only one clear advantage over all sorting algorithms. Can anyone take a guess?
It's easy to code.
It is easy to code. That's its one advantage. That's pretty much its only advantage over every other algorithm, is that it's easy to code. So if you have to code a sorting algorithm and it needs to just work and you don't care about the speed, and you for some reason don't have access to a library, Google, et cetera, you're on the island and you're gonna die unless, the threat of death is there, unless you write a sorting algorithm to sort these elements, just write bubble sort. Yeah, exactly. Right. Then you write bubble sort. Okay. But does everyone see how this works? Hopefully you see how inefficient this thing is, but that's okay. Number of comparisons, hey, it's n-1 plus n-2 plus blah, 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 blah. AKA, the first time you do it, it's n-1 comparisons. Actually, when we did it, we're doing n each time, but that's all right. And that looks oddly familiar. That's because it's the same one, except for you're subtracting instead of adding. The reason why you subtract is in the formula, you don't have n over here, so you missed that one. So that's why it's actually n times n-1. You simplified it to n squared. Number of assignments in worst case, well, you could do assign every time you swap, right? Or every time you compare. So then, yeah, you're back to n squared. So comparisons is n squared, assignments is n squared, which compared to basically every other sorting algorithm is terrible, but that's okay because it's easy to write and everyone's happy. All right, any questions? Oh, yes, you're gonna have plenty of lab time. We have plenty of lab time, and we basically did the lab in class. Yeah. No other questions, comments, screams?